Wonderful. So our last speaker today is Dylan Gayer, who's from Cole College in Iowa, and it's also a starting senior. And this summer, he was working with Pedro Biglini. And I'll give it to you, Dylan.
Right. Thank you. So today I'll be discussing radio emissions of infrared dark clouds, specifically through molecular transitions and continuum maps. So for a brief overview, I'll begin this talk by discussing two main massive star formation models and a region for massive star formation. I'll then move on to my project objectives and what I was working on this summer. And then I'll move to our data set and some results. And I'll wrap up the talk by discussing some big questions that we still have and some next steps. So one thing that we know about massive protostars is that they're more likely to form in these star-forming clumps, which means that they form with many low-mass protostars nearby. The competitive accretion model states that these massive protostars in the clusters form from a low-mass protostar that is at the lowest gravitational potential in the clump. Thus, it accretes more material over its protostellar lifetime. This is shown in the simulated data on the right, where we have a low-mass protostar here represented by this red dot that's at that lowest gravitational potential. So over its protostellar lifetime, it'll accrete all of this green gas and become a massive protostar. The black dots in this region represent other low-mass protostars in the region, and the blue regions highlight the gas that is gravitationally bound to a low-mass protostar other than the massive sink here. So this takes us to the next massive star formation model, the turbulent core accretion model. This model states that massive protostars form in a similar manner to low-mass protostars, in the sense that the initial collapse must bring in enough material to form a massive protostar, rather than the further accretion shown in the prior model. So to make the differences in these models a bit more clear, the turbulent core accretion model states that each protostar has its own independent envelope that determines the mass of the protostar, while the competitive accretion model states that even after forming that low mass protostar, these protostars compete with each other for the remaining gas in the region. So following the massive star formation models, a region for massive star formation is an infrared dark cloud. These infrared dark clouds are cold molecular clouds that are dense enough to block infrared radiation. They are observed as dark spots on infrared images and thought to be hosts for massive star formation. Since the construction of ALMA, there have been many surveys studying massive star formation in these infrared dark clouds. A few examples of which are listed below, such as the Kong et al. 2017 survey, where they studied the N2D plus emission line in massive starless cores in these infrared dark clouds. We have the Lee et al. 2020 survey, which studied CO and SIO outflows from a subset of the massive starless cores identified in the Kong et al. Survey. We also have Liu et al. 2021, where they studied SIO outflows from the massive starless cores, published in the Kong et al. Paper. And in addition to the ALMA data they used for that, they also performed VLA C-band observations of those same massive starless cores. And the final survey I'll mention here is the Purser et al. 2021 survey, where they used VLA to study radio jets in massive young stellar objects and infrared dark clouds. And of course, there are many more surveys on the archives. So my main goals for this summer were to further analyze archive data on these infrared dark clouds, specifically molecular emission lines and structures in their continuum images. So in addition to the N2D plus lines published by the Kong et al. Paper, they also looked at C18O, DCN, and DCO plus lines. And while looking at their data, we found a low resolution spectral window for these sources. So I went through and made continuum images for all the sources identified in the paper to look for bright lines and structures. And right away, we noticed a variety of different structures in these cores. Some have lone bright cores, some have collections of bright cores, some have some dim cores, and we also have very noisy and very clear data. So a classification of these cores is something I'm working on in the future. I've also self-calibrated all of the sources that were bright enough to self-calibrate and still produce a clear image. And after the self-calibration, I looked at the line emissions for these sources, and only 3 sources showed signs of possible line emissions. So we set forth to investigate those sources further. Those 3 sources were B1 and B2 from the infrared dark cloud G01927, and C9 from the infrared dark cloud G02834. And after the self-calibration of these images, we found some interesting differences in their structures. Specifically, B1 has two bright cores that seem to be passing material back and forth. We have B2 with a bright core and then two dim cores. We also have C9 with a bright core and then a two-component tail here. And C9 having line emissions was not a surprise to us, because last year my mentor Pedro published a paper identifying the emissions of the core and tail of C9, as shown on the figure on the right, where we have the core emission on the top and the tail emissions on the bottom. And in his work, he identified complex organic molecules and two sulfur-bearing molecules, namely being OCS 1918 and 13CS54 transitions. And this is a surprise because those sulfur-bearing molecules have intensities corresponding to temperatures of about 25 Kelvin, whereas one of the complex organic molecules has a rotational diagram corresponding to a temperature of around 450 Kelvin. So this led us to believe that there were two smaller sources within that main core of C9. And after overlaying VLA archive data that was cleaned and calibrated by Pedro with my self-calibrated ALMA data, we can see that there do seem to be these two smaller sources within that main core of C9. And we plan to investigate these two sources further. So in terms of B1 and B2, although their emissions are about 5 times weaker than the emissions of C9, we've discovered the OCS 1918 transition, the 13CS54 transition. We have methanol here, and there are other complex organic molecules that we found in B2. And another thing that we noticed is that the relative intensities of these peaks are quite different when comparing B2 and C9. So this leads us to believe that either these two sources have different chemical compositions, or the more likely option is that these two sources are at different temperatures. And as for B1, since it is in the same infrared dark cloud as B2, we believe this small peak here to be a marginal detection of that OCS 1918 transition. So this work has left us with some pretty big questions left, such as why do only 3 out of more than 15 sources show signs of these molecular emissions? What are the physical parameters such as mass and temperatures in these cores? How do those physical parameters align with the two main massive star formation models? So some next steps we can take to answering these questions are by identifying the other peaks in the B2 continuum emission, such as those complex organic molecules, utilize the gray body equation, which is a correction term applied to the black body equation, to calculate possible mass and temperature values for these cores. We can analyze more archive data to get more information about these sources, or even identify other sources with similar emissions. We also plan on classifying those continuum emissions for these molecular clouds and identifying how many have collections of bright cores, collections of dim cores, and extended emissions, that type of stuff. So one step that we have already taken is submitting a VLA proposal under the title Sulfur-Bearing Molecules in Infrared Dark Clouds, along with a collaborator, Dr. Zulema Abraham. And the main goals of this proposal were to detect the OCS43 and CS10 transitions in those two smaller cores in the main core of C9. And we hope to do so with a high spectral resolution to first constrain the temperatures of those two cores, and second, if possible, constrain the chemical compositions of those two cores. We also are choosing to detect the CS10 transition instead of the 13 CS10 transition because of the fact that the CS is much more abundant than 13 CS in these clouds. So another thing that we are looking to gather is 7mm continuum data for those 3 sources, B1, B2, and C9. And we hope we can get the time to detect these transitions and gather the continuum data for these sources. So I would like to thank you all for attending my talk, and I would like to extend a special thanks to Dr. Pedro Biglini for his continuous support and hard work this summer, and to Dr. Zulema Abraham for her collaborations on this project. Thank you.
Thank you, Dylan. Questions? Again, lots of applause. I really should have created like this sound for applause.
Thank you, Katya.
No problem.
Hey,
Okay,
this is Brian. I had a sort of a comment and a question.
Yeah.
When you showed that spectrum for, I think it was B2, had maybe a marginal detection of OCS
Yeah.
in it, or B1.
Yeah.
Yeah, I was, something. Yeah, my astronomer eyes also picked up that there may be features around to the two right of it. But
Yep.
anyways, something you might think about is doing like a cross correlation with a template spectrum, like basically take your spectrum for C9
Mhm.
and then convolve it with the spectrum at the velocity. So
Yes,
something like this. Oh, sorry, go ahead.
we have actually done that and
Oh, okay.
saw that they did align.
Okay, cool. Because you might be able to get more statistical power
Yep.
that way than just within a single line. Yeah. Okay, cool.
Yeah.
Any other question?